Hi, my name is Adolfo Castro Campos, and today we'll explain the experiment of Paul's pendulum. Here you can see an image of Paul's pendulum. Basically, it's a type of rotationary pendulum. In the image on the left, you can see there are two circles, one inner one and one outer one. The inner one acts as the pendulum itself. Here you can see there's a little tick mark, which tells us where is the amplitude in a given time. And here in the other circle, there are the numbers which describe the actual position in the unit called SCD. So pulse pendulum is basically just a rotationary pendulum, which is described by this formula, which is the inertia times the acceleration plus the coefficient constant times the velocity plus the torsion constant times the angular displacement, which all of them should be equal to 0. For the first part of this experiment, we will actually focus on this equation here. This symbol delta means it's called the damping constant, and it's what we're trying to get in this first part of the experiment. In order to know this damping constant, we will use the following formula. The important thing about this formula is this part here, on which you can see it's e to the minus damping constant times time t. And this is basically the amplitude. In order to get the damping constant, we will actually take the natural logarithm on both sides, and we get this formula here. Here we can actually use here the natural logarithm of the amplitude, and use this part here and plot the amplitude against time. Therefore, the slope of the best fit line will actually be equal to minus the damping constant. Okay, so here is the data we used. We actually used two types of two cases of the pulse pendulum, each one with a different current. Here the current is 0.1795 amps, which can be roughly estimated to 0.18 amps. So how we got the data was observing the pulse pendulum rotate and getting each of the maximum amplitudes it got on every rotation. So here you can see a list of the amplitudes. You can see how it's decreasing over time. And here in the second column, it's time, which is actually described as a multiple of the period. This because the data was actually given in periods of 10 oscillations, as you can see here. So for example, for these 20 first oscillations, actually some of these will be a minus sign. For example, here is 17.4, then it's minus 16.6. But here we're actually using the absolute values of the amplitudes in order to get more data points. So that's why each of these amplitudes is only half a period. So therefore, this time will be the correspondent to all of these 20 data points we have. In order to get the uncertainty of the time, we actually took the standard deviation of these values right here. So with this one, we can actually calculate the error bars. So basically, what we're going to do is plot the natural logarithm of this graph here as the y-axis, and time in seconds, not in periods, as the x-axis. Here is one of the data. Here is the other data we got for when the pulse pendulum is at 0.4 approximately amps for current. Here is the same values. Here you can see we have less values because the amplitude decreases more rapidly, so it becomes less and less stable. So therefore we could only get 10 values, and as before, each only represents half period. So therefore, this actually corresponds to this time right here. We use the same process, getting the standard deviation from these values in order to plot the error bars. We plotted the same in the same axis, the same columns. So here are the results for this first part of the experiment. Remember, this is the formula. The best fit line will correspond to an equation that equals the amplitude, and this will be the x multiplied by slope. So here's the value of the slope. As you can see, it's equal to minus the damping constant, as you can see here, for both of these data points. Here is in amps. So remember, this one has more data points because the amplitude decreases slower over time. So therefore, we could get more amplitudes. So as you can see here, it does fit a straight line, roughly. It's more consistent at the beginnings, because if there are a little errors in the calibration of the equilibrium position, they do not affect much the value until the early stages, where it's just a little above that equilibrium position. For example, here, as the difference in the last data points, as the difference is only about 0.4 or 0.2, a little error could create a great error bar. Where at the beginning, that 0.2, for example, for error, it wouldn't affect so much. So here we can see two things. One, they do follow a straight line. And secondly, which will be important for the second part of the experiment, we can show here that the bigger the current, so for example this one, the bigger damping constant we will get. Here was 0.235, etc. And here was only 0.056. So therefore, when one increases, the other one increases as well. Now, for the second part of the experiment, here we will use this theoretical graph in order to explain it. Here on the y-axis is the amplitude uploaded, and on the x-axis is actually the external angular frequency. So what this graph tells us is that when you plot the frequencies for a specific damping constant, we will get this type of graph, which has an obvious peak, and this peak will be this angular frequency, which is the natural angular frequency. So for this second part of the experiment, we actually want to know what this will be using this graph, this type of graph. Basically, we are going to use two different set of values, each one with a slightly different current. And here we, when the peaks align, will be our answer for the angular frequency. Because as you can see here, even though the damping constants are changed for the different types of graphs, here you can see in different colors, they actually correspond to the same angular frequency. Also, the second thing we want to see if the experiment shows is that this relation, that the smaller the damping constant, the bigger the peak, the more accelerated it will be on the graph. So here are both of our values we got. On the first experiment, what is important to see is we use a current of 0.01 amps, and in the second we got a slightly different and lower current of 0.009 amps. Here what we can see the amplitudes and also the time for each of the cycles. So how we will plot this is we want the frequency, therefore it will be 1 over the time because it's in hertz. So this column here will be 1 over the x-axis, and this one here will be actually the y-axis. So when we plot both of these on the same graph, we get the following graph. Here you can see that we get a similar graph that we got from the theoretical one. That there is an obvious peak around here, around this area, And if we get the average of both of these peaks, we get that this is the natural frequency of both of them. Here is the number in more detail. What's important to see in this graph are two things. One, that both graphs, their peaks align roughly the same as the theoretical graph showed us. And secondly, here you can see that the red graph has a higher current. And as we saw before, a higher current corresponds to a higher damping constant. And a higher damping constant, as we saw in the graph, corresponds to a lower peak on the graph. And as you can see here, the higher current has a lower peak on this graph. So when we compare them with the theoretical graph, you can see both of these phenomena explained. One, the peaks roughly align, as we saw here on the graph, where they should be the same for the natural frequency. And secondly, that the one with the higher current has the lower peak. As you can see here, that says that a higher damping constant, which remember is corresponding to a higher current, it's lower than a smaller damping constant. So therefore, our results align with the theoretical graph very nicely. Thank you.